Okay, so it looks like it's recording now. Can you still see my screen? Just to make sure it hasn't cut out.
Yes.
Okay, great. So the first object that we could perhaps analyze is this. So it's a composite function, square root of a fraction. And we need to know where this thing is, say, defined, continuous and differentiable. And so what we've got to be careful about here is the fact that we're doing composition with the square root. And on top of that, we've got a fraction, so you could possibly divide by 0. But if we look at the values of this function, you can sort of make a sign table even on, say, rough notes. And if you look at what 1 minus x divided by x gives us, you can look at the values on R. So if you go from minus infinity, you'll have 2 critical points. You have 0 and 1 plus infinity. So 1 minus x will be negative up till 1, I guess. No, positive, sorry. Up to 1, and then it becomes negative, and x is negative up till 0, and then positive. So you get this. And of course, x is equal to 0 here, and 1 minus x equal to 0 here. So if we consider the fraction, that's equal to, that has a negative sign here. At 0, it's not even defined, okay? Here it's positive, and it's negative afterwards. So it's equal to 0 at 1. And in particular, at 0, it's not even defined. So those are the values of square root of 1 minus x divided by x. So where could we look at this fraction to perhaps solve the inequality?
From 0 to 1?
Yeah, absolutely. We could, if we want to, for example, study this square root more in detail, we have to take values for 1 minus x divided by x where everything is positive. And so we need to restrict ourselves to the interval 0, 1. So that's defined and continuous. On so 0 you have to exclude, and 1 you can sort of take. Where is it differentiable? If you
we have to exclude the 1.
Yeah, absolutely. If you look at the value of the underlying fraction at 1, it's equal to 0, and the square root is not differentiable at 0. So it's differentiable on the open interval. Okay, so that's what's inside the arctangent. Now, can you remember where the arctangent lives and what it's where it's sort of defined as continuous, etc.?
I think it is between 1 and minus 1.
It should actually be on R, I think. I think it's the function that.
Oh, sorry.
Yeah.
I was thinking about arcsine.
No, arctan is the function. Yeah, no problem. You're right about arcsine. Arctan is a function that's very roughly like that. You end up in the end with a function that takes values on the whole of R. So we can state that here. So you get a function that's defined, continuous. Differentiable on R. Okay, so if we take a look at the first part of the function, if you put these two lots of reasoning together, where is this defined continuous differentiable?
On 0, 1, 1 excluded, and 0.
Yeah, exactly. So differentiable 0, 1 with 0 and 1 excluded. and define continuous 0, 1, but you can include the 1 if you want to do defines and continuous. So yeah, exactly. So if we take now x maps to 2 arctan of square root of 1 minus x divided by x, that's basically defining continuous and differentiable on the same spaces as above. Okay, and then we need to take a look at the second part of the function, which should be slightly easier to deal with. So arcsine, I think was just it was just mentioned that you can deal with arcsine on -1, 1, and so that's what we're going to base ourselves on to reason with arcsine. So if we now consider x maps to arcsine, or maybe y, because we're going to do a bit of function composition of y, is defined and continuous on -1, 1, and it's differentiable on -1, 1 excluded. So how can we find where arcsine of 2x minus 1 is defined and differentiable?
With two inequalities, so -1 less or equal to, less than 2x minus 1 less than 1.
Yeah, absolutely. We need to find x such that 2x minus 1 lives in here. So you've got to solve some sort of, I guess, double inequality. You're absolutely right. But -1 smaller than 2x minus 1, smaller than 1. That's equivalent to, if we add 1 on, you get 0, smaller than 2x, smaller than 2, and so you get 0, smaller than x, smaller than 1. Okay, so x maps to arcsine 2x minus 1 will be defined and continuous on the closed interval 0, 1 and differentiable on the open interval, as is the case above here. So there we go. So we've reasoned with the two parts of the function for which we're trying to solve an equality. So where is the sort of final function defined and etc.? So we've got some sort of issue, I guess, with this interval, sorry, and this one aren't exactly the same. So if we let f be a function that maps x to the sum of the two, so we've got this term plus the other term. Where can we study this function in the end?
The intersection between both of the definition domain of the separate functions.
Yeah, absolutely. If you want them, if we want to analyze f, we need to have this well-defined continuous differentiable and this one too. So you need to take the intersection of the domains. And what we get in the end, using the above reasoning, we'll get f defined on the intersection, which actually happens to be the domain on which we can do things for. Actually, that's not quite right, is it? It's this domain here. So 0, 1 with 0 excluded for the definition domain, and both edges excluded for the differentiability domain. Okay, so we now know where we can work with this function, and we know that in particular at 1, we did the calculation quickly earlier. If you take 1, you get f of x equal to pi over 2. So f of 1 solves the equation. How can we generalize that to try and get to check where the equation holds? How can we find where the equation holds apart from in 1?
We can compute the derivative to find that it is equal to 0 and to say that the function is constant.
Yeah, absolutely. Now we know where the function sort of lives. We know where we can derive it. So we can compute the derivative, and we'll end up showing that the derivative is equal to 0, and we'll be able to show that the function is constant. So let's do that. So for any x, if you want to compute the derivative, we take x on the open interval 0, 1. We need to compute f prime of x. So this is where we need the different sort of derivation formulae for composite functions. Let's do that. We have, first of all, arctangent of the square root to derive. So we're going to get 2 pieces for this. We're going to get the derivative of arctangent applied to the square root. And the derivative of arctangent is 1 over 1 plus x squared. And we'll replace x by the square root part. And then we'll have to multiply that by the derivative of the square root. So that's the first part. So we get 1 over 1 plus square root of 1 minus x over x squared times the derivative of the square root. And so we'll should get minus 1 over 2x squared times the square root of 1 minus x divided by x. So that's the first part. And then in the second part, we've got to do similar for arcsine. So arcsine of 2x minus 1, if we derive it, we'll have the derivative of 2x minus 1, which is 2, times the derivative of arcsine applied to x minus 1. And the derivative of arcsine is 1 over square root of 1 minus x squared. So you can see that you need to have all of the derivatives, I guess, sort of in front of you, or if you don't sort of know them yet. If you've got some sort of flashcard with them all, then it helps a lot with these exercises. And you should get the sum of these 2 terms. And so we need to simplify them somehow. So let's do this. First of all, we should be able to simplify that. And that, we've got 2 and 2, and hopefully we can rewrite things now. So we get minus 1 divided by x squared square root 2x plus something that's going to simplify, I hope. You should get something like this, which probably is going to require more simplification, plus the second term. And the second term, we can expand the square in it, so we get 4x squared plus 4x minus 1. Okay, so we get this. We might want to do a little bit more work though. So this x squared here can simplify with this to some extent. So, well, this one rather. You get 1 minus x times x times the square root And the second term, you'll be able to rewrite what we had. So we'll get square root of 4. So you can see that 2 and the square root of 4 will simplify. Factor of x times 1 minus x. Okay. So if I just write the terms in the different order, you'll get 1 square root of x times 1 minus x. And then we need to work with the second term to get minus that. So we get minus 1. Come on, we get square root of, we write can factorize by square root of 1 minus x. You get x squared divided by square root of x plus this. Now hopefully that should simplify to square root of x somehow, which it should do. If I multiply everything by square root of x, that work?
Yes, that works, because if we put the x in the 1 minus x, the x squared cancels each out, and 1 over square root of x. Wait, I don't know.
Don't worry. Oh yeah, wait a minute. I've got it. Not quite, but so we get x squared. If we just look at that, we should get this. And we get x over square root of x, and I should, oh yeah, that gives us square root of x. Sorry, I'm not quite on the best form. So that, if you have a look at what we have here, we have 1 over square root of x minus times 1 minus x minus the same thing, so we get 0, reassuringly. So that's the derivative, which takes a little bit of work because it's composite derivation, and then we need some simplifications. And we see that the derivative on this open interval is equal to 0. So what does that tell us about where the function is constant?
I think it is constant on its definition domain.
Yeah, it's constant on here
0,
is
yeah. 0,
yeah.
1, but 0 excluded.
Yeah, absolutely. From this, you can, if you have a function that's differentiable on some AB, but continuous, for example, on AB that's closed, as soon as you have the function's derivative equal to 0 here, and the function is constant on that domain, in this particular case, we have to exclude A for definition and continuity, but we still have the implication that derivative equal to 0 here means that the function is constant on the sort of slightly bigger interval where the function is defined and continuous. So what we deduce here is that f is constant on 0 excluded, 1 included. And now what value do we know for the function?
The 1 over 2 when x is equal to 1.
Yeah, absolutely. We know that when here, if we set x equal to 1 here, this goes to 0. And this should give us arcsine of 1, which is equal to pi over 2. So, and as f of 1 is equal to pi over 2, deduce that f of x is equal to pi over 2 for any x in 0, 1. So there we go. It's the same sort of reasoning once again, with the slight, I guess, particularity that functions are just slightly harder to deal with. But yeah. Are you still writing perhaps the derivatives or not?
Yes.
Okay, yeah. I think for the final question of this exercise, the interval is actually specified because the reasoning is slightly harder. But we're going to end up doing this one last time in a few minutes. Maybe while we're waiting, I can ask, how did you find Tuesday's test overall? Was it okay or not?
For me, it was
Sorry, what?
okay.
How did you find
Almost
the
I
test
was-
on Tuesday?
It was okay. I guess.
It was okay
It's
for me.
okay.
I just wasn't able to completely finish the last exercise. But that's just because
Okay.
I'm not very good at time management.
No problem. I hadn't specified the any approximate timings here anyway, so it probably didn't help for time management. Yes, I think I haven't looked at them, but it looks like a lot of you have done a lot of the test, so it's quite good. Yeah, the constants in the differential equation are quite difficult though, so that wasn't very yeah, doesn't matter about that. Okay, can we move on to the next question, or are you still writing stuff?
It's fine. You can move.
Okay, thanks. Okay, so in the last question, we're going to come on, take a look at this. So what we're going to prove is the following equality, and we're going to prove the following equality for x in a certain interval that's already specified. So what we're going to do first to prove this equality is just check that here everything's well defined. And once that's done, and in particular we want differentiability still, and once that's done, we'll be able to prove the equality. So we're just going to take a look at the two different objects here, and you can see that they're composite functions again. So first, maybe we can note, where is argth defined? Can you remember?
I think it is on R.
Not quite. It's argth is defined on -1, 1, I think. I think it's arg, where is it? The one that we saw here, above here, arctan is on R and argth is on -1, 1. Yeah, the two are a bit confusing, but I think that's where they're defined. But using that, we can check where we can do things here. So x maps to sine of x, defined continuous and differentiable on 0π/2. And if you have a look at the values that sine of x takes on this interval, you'll get 0 included, smaller than sine of x, and the greatest value that we'll get will be the value at π/2, and at π/2 you should get 1, but we can exclude 1. And then y maps to the hyperbolic tangent. That's defined continuous, differentiable on 0, 1 excluded. So in particular, argth is defined continuous on different, is defined in continuous. Actually, I might want to be a bit more careful. It's defined in continuous on the open interval. Actually, I don't want to say something silly. Have you got the argth curve in front of you, any of you?
Yeah.
Where is it defined?
Well, I think it's from -1 to 1 excluded.
Okay, yeah, okay, that makes sense. In that case, I can do that. Yeah. I think, yeah, you get 2 vertical tangents, like not quite like that, but it'd be like x cubed. Okay. We could write this for -1 with -1 excluded to 1, but we only need it from 0 to 1, so we can stick with that. Therefore, x maps to argth sine of x is defined continuous, differentiable on 0 and π/2. Okay, so that's for the first part. And if we look at 1 over cosine of x, if you have a look at what happens on 0π/2, this thing will be defined continuous and differentiable in general on R, except at the places where cosine goes to cosine of x goes to 0. And here this interval is well chosen, and we'll again get defined continuous and differentiable on 0π/2. And obviously you could find other parts of R for which this function is defined continuous and differentiable, but here we're given a sort of restriction on which to work on, so we can just use those values. Now what happens with argch? So if you have a graph of argch at hand, or if you have its expression, I think it's got a logarithmic expression. The curve actually only starts at 1. The function's value starts at 1, and then it's an increasing function. So it's a bijection from 1 included to, plus infinity to r plus. And I think it's defined from 0 to 1 infinity, but it's only differentiable with 0 excluded. So what we need to check is that the values of 1 over cosine of x on 0π/2 are compatible with the values that argch takes. So we're going to just have a look at the values of cosine of x, of 1 over cosine of x rather, on this particular interval, and we'll see that they're compatible. So we need to prove in particular that that's positive, and always greater than 1. So what you should have, if we take a look at cosine of x, does it have any monotonicity from on 0 pi over 2?
It's increasing. Decreasing.
Yeah,
Sorry.
it's decreasing. No problem. This one is decreasing. We have what that means is that so we have 1 smaller than cosine of x, smaller than cosine of pi over 2, which will be equal to 0. Okay, and in particular, if you actually, that's absolutely the wrong way around. Get it like this. Okay, and now if you want to take 1 over cosine of x and look at its values, what do you get?
We get 1 is smaller or equal to 1 over cos of x, smaller than 0.
You're
Should
right
be.
about that. And it's not quite 0 here. If you take 1 over 0, what would you probably end up with?
Plus
You'll get-
infinity.
Yeah, exactly. Here, you can, if you want, you can add plus infinity here. If you take 1 over 0, you're on to you're above 0, so it's sort of 0 plus, and 1 over 0 plus gives you plus infinity. And so in particular, yeah, is that point okay?
Yeah.
In particular, if you want to, you could just write that implication if you want. Because what's important for us now is we want to take, where is it, argch of this. Argch is only defined on the following. So if we take y maps to argch of y now, is defined continuous on, where is it, on 1 plus infinity, and differentiable on 1 plus infinity. And so if we combine this with the reasoning we've done with 1 over cosine of x, we can conclude the following.
I have a question.
Yeah.
If we had smaller or equal to 0, would we have then 1 over cos of x smaller than 0, or would we still have plus infinity?
So if you had, for example, cosine of x smaller than 0, so
no, bigger, but bigger or equal.
Okay. If you had bigger than or equal, and if you take 1 over cosine of x, you'd still have in this setting, you'd still have smaller than plus infinity.
Okay.
When you take 1 over the function, you inverse the bounds. If the value here, when you take 1 over that value, is well defined, so imagine you wouldn't get this at all ever, but if you had cosine of x greater than 3, which can't happen, you'd then have 1 over cosine of x smaller than or equal to 1 over 3. Okay, but as you end, if you take 0, you've got infinity, and you can't attain infinity, so you can't really write equal to infinity. That's a slight subtlety.
Okay.
Okay, so what we can deduce here is that x maps to, so it's argch of 1 over cosine of x is defined continuous on 0 pi over 2, differentiable on open interval 0 pi over 2. So what we've done is basically analysed, if I just take that quickly, copy, we've analysed the 2 different parts of this function for which we want to get the equality. And we want to somehow use the reasoning that we've used up until now to prove that this equality holds. Do you have any idea about how we could use the previous reasoning and the stuff, so the stuff you've done here and the previous method to do this?
If their derivatives are equal and they have one point where they have the same image, then
Yeah.
they are both equal.
Yeah, that uses things related to primitives and integrals, which is a good approach. So that's a good approach. We can actually, I suppose this basically the justification behind the fact that it works for with the reasoning that you're saying is by the fact that if we take the function that's the difference of the two and we compute the derivative, we get a constant function, and then we can prove that for a particular value, for example, 0, the function's equal to 0. So let us set x maps to g of x equal to argth sine of x minus argch of 1 over cosine of x. So if you want to look at where the functions defined continuous and differentiable, we need to take the intersection of the terms that we had earlier. So we've got this result, and somewhere we've got the other result, probably here. So we're going to take the intersections, and in particular we'll end up with this for the different domains. So G is defined and continuous on the open interval, or not the open interval, but the interval where we include 0, pi over 2, and differentiable on the open interval. So what we can do now is compute the derivative of this function. So let's try and do that. If we take any x at a point where the function is differentiable, g prime of x, you end up with a first composite derivative. So maybe I can write that slowly. So you get argth prime of x applied to sine of x times sine prime of x. Okay, that's the chain rule, minus argch prime applied to 1 over cosine of x times the derivative of 1 over cosine. The first term, so argth prime applied to sine of x, that will give us 1 over 1 minus sine of x squared. Okay, the derivative of argth is 1 over 1 minus x squared, so you end up with 1 over 1 minus sine of x squared. And you multiply that by cosine of x. Okay, that's just the first line here. The second ingredient that we need now is the derivative of the hyperbolic cosine inverse. So hopefully you've got it somewhere. What's the derivative of the hyperbolic cosine? The hyperbolic cosine inverse.
It's 1 over square root of x squared minus 1.
Yeah. You get come on. You get 1 over the square root of x squared minus 1, and if you want SH, it's the same thing with plus signs basically. I'll get SH, you get 1 over square root of x squared plus 1. And so if we try and replace it here, you have to apply this to 1 over cosine of x. So you get 1 over cosine of x squared minus 1. And then we need to derive 1 over cosine of x. So if you want to do that, you get you get minus get u over v. There's 2 ways of doing this. Wait a minute. Minus sine of x divided by cosine of x squared, hopefully. And we now need to simplify terms.
Cancel out.
Sorry?
The minus, doesn't it cancel out? Because it's like a minus.
Oh, yeah, you're right. Yeah, it's minus the derivative, isn't it? So it's, yeah, I think you're right. Thanks. Okay, so we now need to somehow simplify these terms in order to get something that we can actually deal with. So can you see anything that simplifies here?
Yes, we have 1 minus sine of x squared, which is equal to cos of x squared. So we have 1 over cos of x.
Absolutely. So if we just take a look at this, that gives us cosine squared of x. So the first term actually simplifies quite easily. So we get 1 over cosine of x. Then we've got to deal with the second one, which is, I think, slightly more annoying. So if we rewrite things, we've got sine of x divided by cosine of x squared. And so what we need is for this term to simplify to something like cosine of x divided by sine of x. And it should do if we rewrite it. So what we get is 1 divided by cosine squared of x minus 1. And what we can do is basically multiply this term and this term by cosine. If we do that, so if you multiply that by cosine, multiply all of that by cosine, you can then bring cosine into the square root. You get cosine squared here, and you'll get 1 minus cosine, and that will give us the expression that we want in the end. So we get 1 over cosine of x minus the 2 terms that we've got in front times cosine of x divided by a square root again, but we get 1 minus cosine of x squared. And we're almost done then, because this gives us sine of x. So we get 1 over cosine.
It gives us sine of x squared. No,
You get, yeah, but you got the square root on it.
Oh, okay, yeah.
Yeah, so exactly the same reasoning, but just luckily we've got a square root that if you take the square root part, you get the square that disappears. So we get this 1 over cosine of x minus 1 over cosine of x, that's equal to 0. Okay, maybe a little note. Here we can multiply by cosine of x. You get cosine of x is different from 0 on the interval that we consider. And squared of x is positive on there. Had we done this reasoning on a place where sine, actually no, that's rubbish what I'm saying there. There's absolutely nothing to justify in that case because sine squared is positive. Okay, so we get a derivative equal to 0. And so if I just try and project as much as possible, do we know any particular values for the initial function g?
I think we can take 0.
Yeah, we can take 0. It's well defined at 0. So we get arcth of 0 and minus arcch of 1 if we do that. And what does that give us?
I think it is 0 minus 0.
Yeah, you're absolutely right. So what we get, so we get g of 0 is equal to 0. We know that the derivative is equal to 0 on this. So g is constant on 0 pi over 2. And g of 0 is equal to, so let's write it, it's the arg th applied to 0 minus arg ch of 1, and that's 0. So for any x on pi over 2, g of x is equal to 0. And if you look at the equality you wanted to prove, you get that the equality holds. Yeah. So that proves the final equality in the final question of that exercise. Or regarding the exercise, I guess. Yeah, I suppose one thing that you can note is that all of these functions here are sort of calibrated for this to work. But this isn't you very rarely come across functions like this when you're doing math, in the sense that if you ever end up analyzing functions, you're very rarely going to end up with a complicated function like this that turns out to be constant. These are just well chosen examples to apply techniques from math, from the sort of analysis results. One thing that often you can prove in quite complicated settings with the theorems that we've seen is that there exists a C such that f of x is equal to C for some complex C. You can use your results to do that, but these equalities here are really quite special. So they're sort of, I guess, academic examples rather than realistic examples, if you get what I mean. Yeah, so that's the end of that exercise. And I think the only thing that we've got remaining is quite a long exercise. So it's exercise 13. So I'm just going to take that. And we've got time in hand. I can leave those calculations up if you're still writing them. Okay, can we move on to the next exercise or not yet?
For me, it's fine. I
For me,
finished.
yes.
Okay, we have got like plenty of time. So if you want me to project further up or something to show some of the stuff, some of the previous calculations, and do shout out because we can do that. So, but yeah. Okay. What we can, if you don't want me to do that, we can have a look at exercise 13. So it's quite a long exercise. If you have your sort of exercise sheet in your hand, you'll see that there are many, I think, let's have a look. There are sort of 4 parts to it. And what it's going to involve is proving a rule called L'Hopital's rule that you actually may have seen before. I think those of you who were here last year probably saw this in the second semester as well as during this exercise, because it's quite a useful rule to compute derivatives and prove some results. And we're going to prove it in this exercise using the results that we have from this semester. And in the first part, what we're going to do is look at a set of assumptions on 2 continuous functions and differentiable functions. And we're going to consider them such that the derivative never cancels out on AB. And we're going to prove that G of A is different than G of B. Now, does this type of reasoning make you think of any result that you know related to a link between G prime of X being equal to 0 and G of A being equal to G of B, for example?
I think that there is a C in AB, so that f of C equals f of B minus f of A divided by B minus A.
Yeah, that's one of the results that we have, I think that's the mean value theorem, the thing that you've just stated. Yeah, we definitely have that as one of the theorems that we have. We also know a theorem called Rolle's theorem, which tells you that what we know is that if you have G of A equal to G of B, then there exists C in the open interval. So it's D prime of C is equal to 0. And so what we're doing here, if you look at question A, is actually trying to prove something that's almost the other way around. If there never exists a point such that G prime of C is equal to 0, then G of A is different from G of B. So that's what we're going to try and do. And we're going to basically base ourselves on the Rolle, which is the thing that I just wrote, and prove that you reach a contradiction.
Can you just use the contrapositive?
Let me think. You probably
Because
can. It probably
G of
comes
A
as
equals G of B implies G prime of implies there exists a C so that G of C equals 0, and so the contrapositive is for any C in AB, G prime of C is not equal to 0 implies G of A is not equal to G of B.
Yeah, I think you're absolutely right. I think the if you write the contrapositive of Rolle's theorem, you get exactly what we're going to try and prove, and it's probably the case that the absurd type reasoning that you can do is just showing that that you can always have the contrapositive when you have a certain statement. So I think you're probably absolutely right. So there are probably those two approaches to this, with one being quicker than the other then. So if we have a look at our functions, we've got f and g, two continuous functions. A, B, differentiable. On the open interval, and we want anywhere on the open interval, we want g prime of x different from 0. We want to show that g of A is necessarily not equal to g of B. And so there's two ways you can probably justify it. First of all, just to contraposer to Rolle's theorem. We can also prove it manually if you want to, but it comes down to the same reason. So what we can suppose for contradiction that g of A is equal to g of B, then as f is continuous on AB, differentiable on the open interval, and why have I got f? G of A equal to G of B through Rolle there exists some C in the open interval. G prime of C is equal to 0. Contradiction. So G of A is different from G of B. And so you can note can also be proven through the contrapositive Is that what you call it in English? Contraposé. Contrapositive.
Yes.
Yes.
Okay, thanks. Overall. There. So you could either prove it through contradiction, or it's exactly the same thing. I think you can prove it through the contrapositive statement. Okay, so we now know that as the derivative never cancels out, then g of a has got to be equal to, different from g of b. This is quite natural, I guess, because if the derivative never cancels out, then your function's always varying. And so you need to get, your function's never going to be basically equal to the same thing. Okay. What we can do now is base ourselves on this to prove a certain equality. And this equality will be useful later on to prove L'Hospital's theorem. So we want to prove that there exists some C such that the following ratio holds. Now, in general, if you just had f of b minus f of a, how can you write that using one of the theorems that the mean value theorem? I think it was mentioned by one of you like a couple of minutes ago.
It's equal to f prime of c times something, and I can't remember.
It's equal to f prime of c times b minus a. Yeah, that's absolutely right. So you can always, when you're under the right continuity and differentiability assumptions that we're under here, you can say that f of b minus f of a is equal to f prime of c b minus a, and g of b minus g of a is equal to g prime of c b minus a. The thing is that what we don't know is whether the c that we use for f is equal to the c that we use for g to write that statement. So we can't just write the ratio of the two equalities that we just mentioned. We've got to base ourselves on that idea, which is to use the mean value theorem. But we need to use a more intricate function, and we're going to use u of x that's defined here. And that's the last thing I think that we'll probably do today. So we're going to use u of x and try and use the mean value theorem in such a way as to show that this holds. So let's do that. We set u, which maps x to f of x minus kg of x for some k and r. We don't know what the value is yet, and we'll have to specify it at some point. So what we know is that u is continuous on AB, the closed interval, differentiable on the open interval. Okay, that's just a direct consequence of the properties for f and g. So through the mean value theorem, there exists C in AB such that u of b minus u of a, that needs to be equal to u prime of c b minus a. Okay, that's the mean value theorem for this new function u that's defined like this. And we can have a look at what this equality here means. So that means that if you write u of b, you get f of b minus kg of b. minus f of a plus k g of a. That's equal to u prime of c, which is f prime of c, minus k g prime of c, b minus a. Which in turn you can sort of factorize the terms and rewrite them a little. You get f of b minus f of a as a first bunch of terms, minus k times g of b minus g of a equal to f prime of c minus k g prime of c, b minus a. Okay, now what we want to do is, this seems actually quite a long way away for now from the equality that we want to prove. But what we can do here is choose k. Okay, this value k is some real number, and we can specify a value for it if we want to. And we can choose k in such a way as to make our life easier. Can you see any way of doing that? Okay, what we want to do is get an equality linked to the ratio of f of b minus f of a over g of b minus g of a, and also f prime of c divided by g prime of c. Maybe one thing that we can hint to, what happens if both of these terms are equal to 0? So somehow this is equal to 0 and this is equal to 0.
Then A
So
and B
which
are
part
equal.
is equal to 0? I didn't quite get it.
This equal, well, all of this equal to 0 and this equal to 0.
Then it's always true.
Yeah, if that's the case, then you can play around with the equalities to get what we want. So if we set,
Oh, maybe we can set k to be equal to f of b minus f of a divided by g of b minus g of a.
yeah, absolutely. So let's set k equal to f of b minus f of a divided by g of b minus g of a. What do we need to specify to ensure that this constant is, as it's a fraction, to ensure that this constant is a real number?
G of b is different than g of a.
Yeah, absolutely.
But I think that was an indication at the beginning.
Yeah. Oh, yeah. Possibly.
I mean, we had
That's-
to show it.
Yeah, absolutely. Yeah, that's the reason why we had to show it. So we've got this constant for k. So then f of b minus f of a minus k g of b minus g of a is equal to 0. So what that means is that f prime of c minus k j prime of c b minus a is equal to 0. But as b is different from a, okay, this is not equal to 0. This is some real number. So this implies that f prime of c minus k g prime of c is equal to 0. And if we take this further, you get f prime of c divided by g prime of c equal to k. So we've got k equal to something here, and k equal to something above here. K is equal to f prime of c divided g prime of c. That's equal to f b minus f of a divided by g of b minus g of a the first equality is, the second one is this one, sorry, and the first one is the one that's just above. And if you have a look at what we were trying to prove, what we were trying to prove is here. It's exactly the equality that we've ended up with C defined through the mean value theorem for our function u. And that allows us to conclude on the first part of the exercise. So those were just some preliminary questions, and tomorrow we'll be able to finish this exercise and do some things related to L'Hopital's theorem.
Okay.
But yeah, we can stop here for today. Are there any questions related to this?
Yes.
Yeah, go
I
on.
don't understand, how do we know that fb minus f of a, I mean the first part, is equal to 0?
Okay, this bit here. Oh, wait a minute. This.
Yes.
Is that, yeah, if you if I just change, if you write out what it's equal to with the value for k that we've specified, minus k g of b minus g of a, that's equal to, so we get f of b minus f of a, and then we use this expression for k, minus, so we get f of b minus f of a times g of over g of b minus g of a times g of b minus g of a. Okay, so I replace by k, and then you can see that as g of b and g of a are different, they're not equal to 0, you can simplify by them, and you get f of b minus f of a minus f of b minus f of a, that's equal to 0.
Okay, thank you.
You're welcome. Okay, we're done for today then, if there aren't any other questions. So I'll try and get a Zoom link to you this afternoon with these notes so that you've got them. And yeah, tomorrow we'll finish this exercise, and then from the second class onwards until the end of the semester, it'll be Anthony who will take you, and I think once we've done this exercise, he'll do sequence things with you and integrals. So you're almost done with maths for this semester. But yeah, we'll stop there for today. So have a good afternoon, and I'll see you tomorrow.
Thank you. Bye.
Goodbye.
Thank you,
Bye-bye.
bye.
Thank you, bye.
Thank you, bye.